Hello everyone. My name is Freya Blekman and I will take some water. I will talk to you about the Large Hadron Collider. And I will focus quite a lot about why we do the science that we do at the Large Hadron Collider, with maybe some juicy anecdotes in there as well. And then also a bit about how we actually look at these collisions. So hopefully most of you in this audience know most of this slide already. So when you talk about particle physics, you talk about the smallest of the smallest. And that builds on years and years and years of science. So here you have sort of a summary that I made, which is trying to summarize our present knowledge of the atomic and subatomic world, focusing also particularly on what we do not know, because I think this is much more interesting than what we do know. So for example, we do not know how small the electron is. We just know that it's smaller than that. We know how big a proton is. That's great. We also know how big a neutron is, by the way, but we do not know how big a quark is, or at least we have limits on how large a quark is. So that's if you go from the size of an atom to the size of the nucleus in the atom to the size of the protons and neutrons in the nucleus to the size of the quarks and the electrons that really build the atom. So there's quite a lot of interesting questions there, and that immediately feeds you into what particle physics, why we do things the way we do, which is if you want to measure things that small, you need to go, fortunately I'm tall, but not tall enough, so you can see the Heisenberg uncertainty principle here. So to measure something that small, you need very, very, very high momentum, or very, very, very high energy, or very, very, very high speed. And that is why we work with colliders. So the goal of particle physics is in principle the same thing as the goal in some sense that chemistry had at a certain time. What is, we see all these particles and we try to find sort of a system in there. We try to find a structure. And now here you see, of course, the famous table of Mendeleev. And the reason why Mendeleev got famous is not because he made a table, but because he explained the structure of the table. So he could explain that essentially each of these columns has to do with the number of electrons that are sort of in the different layers around the atom, right? That's really what in principle, what this structure is. And our work is something very, very similar. And here you I try to give a nice representation of our Mendeleev table in particle physics, which is called the standard model. I will show you a much more horrible version of it soon, don't worry. Now, one of the problems that we have in particle physics is actually we can put things in a nice table like this, but we cannot explain the structure, particularly not the structure of the masses of the different particles. So we know that we have different kinds of particles, we know that, and here in this specific table they are color coded, so there's red particles and green particles and then the blue particles, which are the force particles. And then there's the Higgs boson that keeps it sort of all together. But we do not really know why we have, for example, why these particles always come in these three generations. And we also don't really know why these particles have different masses. So for that, we need these machines to study these particles at as much detail as possible. And here you see actually the front page of Google in 2008, in September. I quickly made a screen capture. For those of you who are young, you can see this is an old page of Google because of the horrible pixels. So, and the retro font. Yeah. So, really an advanced search, you can really see it there. So, and I really like this picture because this is how I look at a collider. A collider is a search machine. And it's a search machine that tries to understand what is inside things and tries to measure the structure of particles. And there's many different ways you can do that. And indeed, most of the ways we do that is really with the brute force approach. And the brute force approach, of course, when you think of brute force, you think of these nice Neanderthals. And they also already had colliders. And here they are trying to understand if there is something inside their rocks. Now, if you look at what is inside rocks, of course, you can collide and you can see rocks break apart, and you can see that they become smaller and smaller. But these Neanderthals also bring up one of the biggest problems in particle physics, which is the fact that we have so many collisions that random things just happen. So just because you see something once, it does not count for us. We really take our statistics very, very seriously, and we try to protect ourselves against statistical artifacts by colliding many, many, many times. And then eventually you can usually make conclusions about whether a particle is fundamental, or whether you can measure things, or you can study the different properties of different particles and different forces, but for that you need a lot of data. And when I say a lot of data, I really mean a lot of data. So for that we need extremely powerful and extremely intense accelerators. And of course, at the moment, the accelerator that is operating at the highest energy and the highest intensity, for that matter, is the Large Hadron Collider. It is just still operating because it's going to turn off this summer. And then we're going to upgrade it again, and then it's going to be off for 3-4 years, and then we go again. And what we measure there and what we try to see are the interconnections with the particles that we know in the standard model and with the 4 fundamental forces. 4 fundamental forces? Well, not really, because the standard model is not good enough to do all 4 fundamental forces. Gravity, which there was a very nice talk about before that also spoke about relativity. One of the problems that we have is that particle physics, because it's a quantum theory, is very, very difficult to combine in an easy and in a testable way with general relativity. So for us, at least for the energies that we work on at the Large Hadron Collider, we really only try to study the 3 forces that we know that we can probe with our colliders, because at the energies that our collisions happen, we know already that we will not be able to do gravity. So now I get a nice little question mark. We don't understand this link. So this link between gravity and the quantum world is one of the biggest questions, of course, at the moment in physics. And I will not talk about that because I'm sure there's plenty of people. And I also know that this is quite a controversial topic, so I do not want to get into the discussion about the different kinds of quantum gravity and string theory. So get yourself a quantum physicist who talks about that. So let's talk about the standard model. The standard model... we are quite proud of the standard model. The standard model is often given as one of the biggest successes of physics, one of the biggest achievements, and like one of the very, very precise theories that there are in physics. And that's true. But I want to first talk, before I start talking about that, I want to talk a bit about how we actually measure the standard model, because I think there's interesting things there to be learned that we don't talk so much about anymore, and that are also very important to appreciate, particularly for the younger particle physicists in the room. And most of the detection that we do is based on more or less on the same idea, and it has been for a very, very long time. So when you measure a particle, and yes, of course, I know this is not a particle, this is a plane, but the principle is exactly the same. So we never see these particles directly. We always see what happened when this particle passed through a gas or passed through material in some way and leaves a little signal. And then we measure these signals. And there's been quite a lot of Nobel Prizes actually that have been awarded just for these signals and just for measuring particles in different ways. Very often combined with a discovery where half of the prize was given to the tool that was needed to actually push science forward and see these particles. And then the second half of the prize was given to the person who then observed the particles or calculated the particles or predicted the particles. But all of these principles, they are all dealing with the fact that there is a phase transition of some sort where you have a system that is in a very, very delicate state. And when a particle passes through, it changes or it ionizes, and that current is what's being measured. or that transition is being measured in this case of, for example, a cloud chamber. And this is still the case, that all our detection techniques rely on that, even though these prizes are from now. You can see it from there. Some of them are very, very old. And I would say that in some sense the only exception to this is the recent prize, which the particle physicists also at least sort of embrace, which is the machine learning physics prize of last year, because we are one of the fields that have been spearheading machine learning for a very long time, and I really love using it because it's such a powerful tool, even though, of course, the deep learning machine learning prize, these people were really on the mathematical and the computer science side, not on the particle physics side. So, as I said, phase transitions, all of these different things, except maybe for freezing versus melting, all of these we use to see when the particle passes through it, to change this phase and then measure that. And for each of those steps and for each of those particles, there are different ways to detect this. And that's the principle of how a detector looks at particles when you look at it at a collider. So here you see a very schematic detector. I will say that it's a schematic detector coming from somebody who mostly works on a CMS, because for those of you who don't know that, you can see that it depends on where the magnet is. So so each particle that we know and that we can easily measure when you look at a collision leaves a different and very distinct signature in these detectors and in the different layers where the ionization patterns and the detection techniques are very, very finely tuned to see these particles. Now, it never is as easy as this, because of course this is a schematic, and by now a lot of the deep learning and the other machine learning that we do is actually to interpret very, very, very complex collisions and then extract all of these individual particles to actually see what really happened at the collision. So that leads me to one of the big experiments in Geneva, which is the Compact Muon Solenoid. There are two big experiments. The other one is Atlas, which is where the people in Sweden work on. But here you see CMS. CMS stands for Compact Muon Solenoid. Here you see me. I really like yellow, as you can see. And you can also see CMS is not compact at all. It's only compact relatively for a detector. It's a huge detector. It is called a solenoid because it is a coil magnet, so it only has one big magnet that we use for everything, and it's very good at muons, that's measuring muons, that's why it's a muon solenoid. So, Atlas is twice as big, so if you want to compare how big these detectors really are, then you go into a comparison. So if you want to define CMS as compact, this is likely what you would do, because here you have a building that some of you might recognize, but it's a 5-story building at CERN, and here you immediately get some idea of how big these detectors really are. They are very, very, very big, and they are completely instrumented with detectors that all rely on these different detection techniques of how to measure these particles. So let's go back to the standard model now that you have learned how we actually measure these particles. So when you talk about the standard model, I already showed you this pretty picture. Here you see another way to represent the standard model, which is the formula version. Even this version, I think it's very nice in the sense that it is sort of the PR-friendly version still, because sometimes we also need to just see the standard model in its gory, formulaic greatness. So this is actually the standard model. And for those of you who like mathematics, the only difference between this one and the version on the mug is tensor notation. So I hope you all paid attention during your linear algebra, because that's what gets you from the mug to this picture. And this is obviously a very, very, very impressive big formula. But it's also an incomplete formula, meaning it cannot answer some of the biggest experimental questions we have at the moment in science, in particle physics and fundamental physics in general.
Is this a Lagrangian?
Yes.
Okay, you didn't say.
Sorry, I did not say because it is an outreach talk. Yes, it is a Lagrangian. That is the standard model Lagrangian. First you saw it on the mug in the tensor notation, and then you saw it in the sort of written out notation after that. And so these big questions, and these are all experimental questions that the standard model cannot explain. So there's many other questions that the standard model cannot explain, but many of these are more driven by theory opinions, depending on how you want to look at it, you can have more opinions about this, but I want to talk about facts. So what can the standard model not do? The standard model cannot explain dark matter. Considering that we know that a substantial fraction of the universe is dark matter, and it's a lot more than the normal matter, and then you of course also have dark energy, which the standard model also cannot do. If you actually look at it, the standard model can really only do a very, very small fraction of everything that the universe is made out of. So it's all very nice when we put our standard model on our t-shirts and our mugs and say this is the best formula that we ever made in physics and aren't we proud? But we can do 5% of the universe. This is really not so much, and I think that's a big problem. And of course, that's also why I think it's very, very good to continue asking questions about the other 95%. So as I also said, the standard model also cannot really explain the, and I will go a bit faster because otherwise I will run out of time. The standard model also cannot really explain some other big questions. So particle physics and particle collisions, even the collisions we get at the Large Hadron Collider. Every second we collide 40 million times, and actually each collision is not even one collision. Nowadays it's like 70, 80 collisions, and in 5 years it will be 200 collisions. So we get a lot of collisions. We have statistics, and we see, when we compare matter and antimatter, we see only very, very, very small differences. That's very strange, because of course we are all made out of matter. So nobody really knows where the antimatter has gone. And antimatter has been around for a very long time. We have known it. It was actually predicted that it existed, and predicted that it was existed symmetrically. And it is almost the same as matter. Almost. There are differences, and we see that there are differences, particularly in the weak force. So that means the force responsible for, say, the burning of the sun, radioactivity, things like that. But they're really quite small and very, very subtle, and we've measured them. And they are not able to explain why we only see matter around us. So when you assume that the collisions that we make at the Large Hadron Collider are the same in physics as the collisions that happen between particles at the Big Bang, which is a very reasonable assumption, then there is too much matter. Or we have lost the antimatter, and we do not know where it is. And this is, one, as far as I'm concerned, one of the bigger questions there is in our field. One of the other big questions, as far as I'm concerned, is the physics of neutrinos. So everything I talked about, including that formula there, that you saw before, independent of whether you get the nice version on the mug or the big tensor, non-tensor version, none of those really work for neutrinos. You cannot make neutrinos have mass, which has a Nobel Prize, and it's proven, in a very, very easy way in the standard model. You need extra particles to do that. Particles that we have not seen. Or to put it for the particle physicist, you can't do neutrino masses with the Higgs mechanism. I would also say that one of the very big other questions that we have is the fact that the strong force, so one of those three forces which we claim to also understand, we actually don't really understand so well when you really start looking at small scale. This also has to do with the fact that to do the calculations is actually very, very difficult. So sometimes it's not even really possible yet to test whether this is true. So the strong part of the standard model is substantially less well understood as the other section of the standard model. And then last but not least, as I said, the structure. So why do we have particles that increase in mass? Why do they seem to come in groups? Why do these groups have different masses? You could say, okay, we've discovered the Higgs boson, so we know now that the Higgs mechanism, I've used to work in Belgium, so maybe I should say the Browtag-Blair Higgs mechanism, but that this mechanism explains the fact that these particles have mass, which is true and is an amazing discovery. But that just rephrases the question. The question now has gone from why do these particles have mass to why does the Higgs mechanism give these particles different mass? We do not know that. One thing that's also quite important to know is that, as I said, a lot of these collisions, to actually understand them at the level that we can have play things out against each other. So the particle physics that we do also directly links to the physics that was happening very, very, very just after the Big Bang. You can see the number of seconds. This is very, very, very shortly after the Big Bang. And at that time, these particles were all existing essentially in the same way as we do at the collider, as we see them at the collider. It's just there were many, many, many more of them, of course. We complain about our 200 collisions, but compared to the Big Bang, that's still peanuts. Huh? So the Higgs mechanism was originally actually not even really meant to explain the fact that these particles, so the fermions, the matter particles, that they had different masses. That was something that was more or less an afterthought. The thing that the Higgs mechanism was intended to do was to give the interconnection between the different strengths of the different forces, which was at that time already thought to be related to other particles called gauge bosons, and to explain why the electromagnetic gauge bosons had no mass, while the weak strength particles did have mass. And that is actually the trick that both Broughton, Layers and Higgs used to create to do the mathematics of spontaneous symmetry breaking that they used to predict the Higgs boson eventually. So there are other links to that in some sense, in the sense that this mechanism, that these forces sort of started to decouple, and that the particles were gave mass, is another phase transition. And this phase transition, this is actually a graphical representation of that phase transition from a theory paper in the sort of the soup just after the Big Bang, so those seconds after the Big Bang. And at that time, you slowly saw the Higgs mechanism turn on. And the interesting thing is that connection between those sort of bubbles creating particles with mass, you could actually see also in other ways that you can connect them. For example, through gravitational waves, like at LISA. So I hope that I've convinced you that the standard model is extremely powerful and still has quite a lot of experimental problems that we hope to, of course, solve in the coming years. But some of these questions are so big that I don't think we will solve them anytime soon. But when we actually try to measure the standard model, we don't really measure it as easily and as nicely as you see, even with these beautiful detectors, even with these very, very, very fancy accelerators. And that means, well, why is it stopped? That means that when we try to map the standard model, we need to deal with mapping what we see in our collisions to this formula, which is not so easy, because these collisions, here is a collision from one of the results I actually work on in CMS. This is what they really look like. So this is a collision where 4 quarks were made, hopefully. And you see, each one of these yellow lines is one charged particle. Each one of these blobs is like energy that was stopped of a particle that was stopped by one of the subdetectors. Some of the detectors, like the muons, went quite far. These are very, very messy collisions. And when we try to measure collisions like this, we try to then compress very often with lots of artificial intelligence in many of the steps here. We try to compress these into something that we can sort of quantify. So one of the things that we can quantify is, for example, when you measure the number of particles in a collision, you can measure the invariant mass of all the 4 particles. So what you do is you add the 4 particles up, and I don't know why it stopped. There we go. So when you do that, and you try to sort of combine particles in your collision, you start to see structures, and those structures, they are related to different things that can happen to different parts of the standard model. For example, you can make different particles, and you see that sort of happening here with this blue bump, where you can see that suddenly it's possible to make more than one Z particle in your collision, and then you can start to see it, or you can make one Z particle, which is this other big blue peak. But one of the other things you can do is to look for other particles that maybe create things in a certain way. And this is one of the discovery plots from the Higgs boson, because all these Z particles you see, but obviously, and yeah, we made it sort of easy for you to see by putting a big red peak next to it, the Higgs particle also can make this signature. And when we started to look for the Higgs particle, this is one of the golden signatures, and we tried to see, do we see an extra peak? Now, it's pretty clear if you would just only have the blue stuff that there is an extra peak. And that is the peak that we actually used to claim discovery of the Higgs particle, together with Atlas, by the way. So now we can measure the Higgs particle already much more accurately, because of course the Higgs boson was discovered in 2012. And the Nobel Prize was in 2013 or 14, I forgot exactly. It must be 14 because...
13.
13, thank you. And now, of course, we do things already much more precise. So here you sort of see the cutting edge. To be fair, the cutting edge with the data taken up to 2018. So not that cutting anymore. But where you see what we can see as far as the consistency of the standard model. Like I said, we do not understand why the standard model gives particles different mass, or why the Higgs mechanism gives particles different mass, but we do have a formula that if a particle has a certain mass, then we should know from our formula how often it should interact with the Higgs boson. And this we can measure, and that's what you see here. You see the standard model prediction is this sort of diagonal line, and depending on the mass of each of the standard model particles that we can measure, we can then check if the Higgs boson is really doing the right thing. And you see all these points for all these particles are really sort of on this line, but this is particle physics, so we want to do things precisely. So here you sort of see in the plot below, you can see really how well it agrees. And so what we can really say at the moment is that for the particles we can already measure, which is not every particle in the standard model, that things agree within sort of 5 to 20% depending on the particle. For standard model physics, for particle physics, that's already an amazing achievement compared to 10 years before when the Higgs boson was discovered. But there's still, this is not the precision that we're typically familiar with. And I would also say that most of the more ambitious predictions that are still realistic of the standard model, of extensions that explain all these other big problems, they predict deviations from the standard model that are much smaller than this. So this is one of the reasons why we want to measure things very, very precisely. Now, when we measure things very, very precisely, we always have to solve very, very difficult problems. So CERN does basic research. We do these things because we think it is interesting. But when we try to solve problems that are so complicated, we regularly have to also improve our tools. So we do, in principle, do basic research or why research, but we regularly have to do applied research, how research, just to make our detectors better. So some examples of that are, for example, are in all this computing that is necessary. Every collision that we take at the Large Hadron Collider is approximately 1 megabyte. So this goes very, 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 very fast when you want to save your 40 million collisions per second. So that's not going to happen. So we can only save about a few thousand collisions per second. Just that's already gigabytes per second. That's already super, super much data if you take that data like that years from now. And this is actually what is limiting some of our physics potential, is that we have to throw away collisions. And you may wonder, how do you throw away collisions if you do not know what you're looking for? Well, that's because we also select collisions that we of the particles that we know, because, for example, the Higgs boson, we know how it should behave. So we are very, very certain that we know up to a certain level how a Higgs boson should look like. So those collisions, if we see anything even close, we save it. We make about 1 Higgs boson, I think it's every 10 seconds. So that's under control. And but for some of the other particles we study, they are made so often that we really have to throw some away. And in the end, we really have to make hard decisions there. And yes, also there we of course use all sorts of artificial intelligence to sort of help us with the decision making and make those decisions smarter. Now, one of the other, of course, very famous examples is the World Wide Web. I hope all of you have heard of it, but it's another spin-off effect of particle physics that was just there more or less to help us communicate our data between scientists better. And because of the way that we work in particle physics, which is super, super open, and we really try to always share our data between institutes, and it's not hidden like in many other fields where the sort of institutes hoard their own stuff and not give it to other groups. Everything is in principle shared, and for that you needed things like the World Wide Web already in the early 90s. Nowadays, of course, we use much fancier things. For example, the Worldwide Computing Grid, which is a way to send data between universities really without even realizing what is happening. So in other words, this is like the Google Drive of particle physics. I think that's not a very nice way to put it. But what is definitely true is that if I want to look at my data, I really don't have to worry whether it's in China or in the US or in India. I can just access it. It doesn't matter. Because we need to measure these particles so accurately, we regularly have to make innovations that are also relevant for other people, and that very often then become interesting for the rest of science. And there's many examples of that, things that we had to sort of work on, that we needed to analyze our collisions, that then turn out to be useful for other people. And I would also say, I think one of the most important things that particle physics uses is the people. Or produces is the people. Now, of course, people are not a product, Freya. This is true, people are not a product. But I can tell you that out of all the people that do particle physics, the skills that they acquire, that they then go use in the rest of the world, is probably one of the most influential things that we do actually offer to society. So with that, I'm slowly getting to the end. Particle physics is a field that seems to always work on long time scales. This is also true for the Large Hadron Collider. The Large Hadron Collider will run in a few runs. And we are now just at the end of run 3. And every time we go to a next run, the amount of collisions that the Large Hadron Collider produces goes up. It grows exponentially. So the collider becomes more intense. The collisions become more interesting in the sense that the rare particles are produced more often just because we collide more. It's not that the particles get suddenly produced more often, it's just that we collide more, so we get more rare particles. And if you do that, and you look at the total amount of data that we're eventually going to collect with the Large Hadron Collider, and even now, after having taken data for over 15, 16 years, we only have taken 15% of all the data that the Large Hadron Collider will produce in its life. And I think this is a very important thing to remember, particularly when people talk about the Large Hadron Collider and people are still, we haven't heard anything from them. This is also because these colliders take a very long time to ramp up, and also because some of the physics that we do and some of the things that we study are so super rare that we really need a lot of collisions. So there can really still be surprises. And I wanted to close with the fact that if there are surprises, it is very important to design machines that can deal with surprises, because particle colliders take so long to design that you need to more or less start designing them sometimes before you made the previous discovery. And that means that we very often deal with very, very hypothetical scenarios where we try to design machines that can do a lot of different things, which is anyway important because these colliders, they're not supposed to only do one thing. They're supposed to do many things so that thousands of physicists can all do their thesis and do something that is actually interesting. And that's why we are currently thinking, and I don't know if many of you saw the press release, that we're thinking about what to do with the next colliders. And at the moment we're in the stage where CERN has made a priority list and has made a shopping list. And the shopping list has an amount on it, and the amount is not consistent with the CERN budget. Yeah, this can happen. Huh? I don't know if you've ever made a budget yourself. So now the idea is, how do I make my budget fit? Or do I get like a cheaper model? Or anything in between. So this is the case, this is the state that we are in now, to sort of think about what the next collider could or should be. So with that I want to end. I hope you learned something. And thank you for your attention. And I'm sure there are questions. Go ahead.
You gave the example of medical application. Is there an energy application, the fusion reactor, anywhere in reach with artificial intelligence like you also mentioned?
So I think for a fusion reactor you need very different things than for a particle physics reactor. Most of the challenges for fusion reactors are actually about intensity, about getting enough particles close enough together that and keeping them enough together in a system that you can still take the energy out. So the challenges they have are very much about building containment machines, those tokamaks, right? Where you can keep particles long enough and that have strong enough magnets that you can keep the particles close enough together. So there are of course links, particularly in magnet design and in building materials, but what we do, we have like a few particles compared to them. Well, they go as much blob as possible. So the links are more or less more on the engineering side than they are on the hard physics side, I would say. Yeah. There must be other questions. So it was all clear. Now I know there's many particle physicists in this room, so I hope you learned something about how you can explain the weaknesses of the standard model, which I think is very important to talk about instead of just talk about how great the standard model is. We like to talk about how great the standard model is, and I agree the standard model is great, but we should really also be fair and talk about the fact that the standard model may be fantastic, but it's definitely incomplete. Yeah? Hi.
So you talked about the mystery of the masses of the neutrinos.
Yes.
Can you say something about the masses of dark matter and how that relates to the Higgs? Do you have any?
I wish.
Yeah.
No, but it's definitely true that there are, of course, particularly because the way dark matter is measured, many of the ways dark matter is measured in astronomy has to do with the fact that dark matter has mass. So if that's true, dark matter should also interact with the Higgs particle or with the Higgs field. So that means that precision measurements of the Higgs particle can really directly give you insight in dark matter, particularly if you can find out how often a Higgs particle is made and how often it then fell apart, decayed, into particles that you could not see because they were dark matter particles. So this is why it's super, super important to have a very, very controlled environment where you can easily see that you made a Higgs particle and whether that Higgs particle decayed to something that you could not see. Which is one of the big questions, of course, of future colliders. This is very, very difficult to do at the Large Hadron Collider because of the fact that there's so much extra stuff flying around. So if you made a Higgs particle and you're not certain what it decayed to, there will be other things happening there. So if you're very lucky, you can even say that you made a Higgs particle. That's already pretty good. But then measuring very accurately what happened after that is not so easy. So that means we cannot measure the Higgs decay to invisible particles very accurately at the Large Hadron Collider. Yeah, that's you, Rebecca. Go ahead.
So I have a question. So you put us here at CMS at DESY. What are you guys doing at DESY?
Ah! So yeah. So I think that science communication is also very important, and I will talk about that tomorrow about for the physicists at the Commenta workshop about why particle physics is important. So one of the things that we are doing at DESY, mostly because and the rest of the professors think that it's very important that also early career scientists have a way to learn how to communicate their science. And nowadays, of course, a lot of the ways people communicate is over social media. So we have a group account where everybody can post. So that means that we have bachelor students, we have professors, and we all post there. And the only rule we have is it should be correct and don't embarrass us. And that means that this is a very, very interesting account also to see what life as a scientist is really like. Because yes, we do actually cover the fact that we have something very close to a Swedish fika on Fridays. And we have very nice cakes. But we also really talk about what people did for their PhD. And I don't know if you know, in Germany we get very nice hats with all sorts of things made on the hats. And those are discussed as well. But also we talk about our papers. We talk about our conferences. We talk about really what life is like as a scientist. Because the science, as far as communication science, to explain to the outside world why physics is interesting and why science is interesting, so even going much broader than physics, has links also to making scientists more humane. We are trained as scientists to be extremely formal and to only talk about our results. And that's great between scientists. But if you want to convince a young person or a science denier or even a politician to give you money, you need to talk about feelings. You need to talk about yourself. You need to talk about why this fits into the big picture. And this we do on this account. And the people in our group, and our group is very large, it's the largest group after CERN on CMS, so there's 90 people in it. They really get a chance to do this. And because we pool things, instead of encouraging every young person to start their own account with 10 followers, if you do this, we have bachelor students, master students, PhD students who can talk about their thesis, and 10 to 20 to 50,000 people can actually see their result. And I think that's a much nicer way to teach them how to do this than if they just need to first start up their own account and do this for years and then finally somebody will pay attention. So follow us, get inspired. I think it's a very nice way to do communication. It is innovative in the sense that we really try to not just talk about the science. And that's why I advertise it as well. There was another question? Oh, no, I see people making applause signs. So is one question allowed?
One more.
No.
Okay.
You already asked a question. So if there's anybody else, that is you. Go.
Okay. There's a theoretical physicist, Ulf Danielsson is his name, right? Is it? In Uppsala, he's very popular scientifically explaining, like you say. I don't know if it gives emotion to it, but I think it puts in a very simple and relational way to the public in the radio, for example, and that attracts the audience and makes it down to earth.
This is very, very important.
Yeah, I don't know if you know this, Professor Ulf Danielsson. Is that correct? The name?
Yeah.
Yeah. You know him? No?
Yeah, I guess if he communicates in Swedish, I will not.
No,
Even though I have a very Nordic name, I do not understand Swedish. So,
in Yo-Yo. Okay.
It's not exactly our field, but it's close enough that he knows about our
Yeah.
field.
I'm sorry.
no, but it's like I said, these things are super, super important in many ways, because I'm sure maybe for all the physicists in the room, raise your hand if one of the reasons you studied physics was because somebody inspired you in a newspaper, in a science museum, or something like that. It's all of us. All of us did it because of that. So it's very, very important to, or almost all of us. The rest, I assume, are just shy. So, we need to give this also back to society. And of course, nowadays, a lot of this communication, whether we like it or not, and trust me, I also don't have, I am on social media really in a professional basis. You will not find my private life on social media. I have opinions about that. But communicating this kind of way on places like Instagram and media like that is the same thing as in the 1990s being in the newspaper. This is how you reach people. This is how you get them excited. So with that,
Thank you.